Is anybody following what's going on in Libya? Well, the latest is that Gaddafi is hunkering down and holds Tripoli, which is the capital city, and he has militia people from south of the Sahara who've come up from probably from Chad. They're speaking French, so they're thought to be from Chad, but they're mercenaries, and so their only loyalty is to him. So they're out shooting people as they're going house to house and pulling out suspects. It's really it's a terrible situation, but he seems to have lost the rest of the country. Ricardo?
I read the death toll so far since February 15th was over 2,000.
Yeah, okay. Ricardo heard 2,000 as a death toll. The death toll ranges upward from 200. And what you sort of find after you've kind of followed a few of these things is early on nobody really knows. But I think that probably the numbers of 200, those have been the numbers for the last 2 or 3 days, so they're probably very conservative. And your number is probably closer to right. Yeah?
It's been mentioned to me about a half hour ago that this is thought that he's been killed.
Well, that's news to me. I haven't looked at it. She says within the half hour ago, there's a rumor that he might have been killed. So I hadn't heard that. You could imagine that. Well, actually, an Egyptian Muslim cleric issued a fatwa which says anybody who can kill him should. So who knows what's going on? And in these sort of revolutionary situations, it seems like always there's a fog it's like you're trying to see it through a fog and you can't tell what's going on, and people have different ideas and you never know. So what we're seeing right now is current events unfolding, and the historian's view is going to be much longer. You know, in a year or 10 years or 50 years, people will know a whole lot more about what happened, and you'll be able to put it together. This is what John Gaddis was talking about in the Landscapes of History book about seeing things dimly when they're actually happening. But the historian also likes to see what the background to it is, and I thought I would just show you what I've been looking at lately, and hope that this will inspire you to do the same whenever you encounter a situation in current events or anything else that intrigues you, to look at it with the historical mindedness that we've been talking about. So I thought I would show you two interesting things about that country as just a sort of a little warm-up for today. So here is the country of Libya again, and I think, yeah, over here you can, if you're in the right place, you can see the borders of the country there. And so this is Egypt, this is Tunisia, Algeria, and there's Libya right now. Well, the reason that this country matters to the rest of the world is that it's very rich in petroleum. So I thought I'd show you what that looks like. This sort of a great embayment in the coastline here is called the Gulf of Sirte. And the onshore part down here is where the oil is, and so that's called the Sirte Basin. That's S-I-R-T-E. So I thought I'd just show you what one of these places looks like. So if we, hopefully, yeah, it's working. Okay. So that's going to gradually zoom in, and if you pan around there, you'll see an awful lot of desert, and in places you'll see oil installations. So I found a number of those this morning as I was poking around at it. But just kind of zoom in. So how many of you have really played around with Google Earth? So those of you who haven't, this is just an absolutely rich thing to explore. So here we're zooming on just one that I came across by chance. So here is an oil installation right here. And you can see some tanks there and pipes of various kinds going around. This must be, imagine this is a wellhead here, and they're flaring off gas. So the wind is blowing from the south and blowing the smoke off in that direction. Okay, so there's a lot of that in the Sirte Basin, and Libya sends quite a lot of oil out, and it's particularly fine oil. It's what they call light sweet oil, which means it doesn't have a lot of tar and heavy sulfur and things like that in it. So it's very, very prized in the West. All right, so now let me show you something else. How many of you have been up on the 3rd floor of our building on the next aisle over? Not this aisle, but the other. Go and look at it. There's an incredible satellite image of all of North Africa, from Morocco all the way across through Egypt and then through Iraq and then on into Pakistan. It's an incredible image, and I just love to go and look at it, and I see all sorts of things. So I want to show you one thing that I saw one time. There's some circles there, so let's go look at the circles. So we're backing out. So this is the Sirte Basin, and we're going to move farther south into the desert of Libya and see something that's really peculiar. And now, can you see on the right hand side there's some sort of lines of circles that don't look like they're part of the natural desert? Well, those are part of what we're looking at, but we're going to move into an oasis down here called Kufra. And oasis is a place where there's some naturally occurring fresh water in the desert. And you see these things? Aren't those remarkable? So there's the oasis. And these are circles. What do you think they are?
Agriculture?
Matt's got it. Okay, so this is agriculture. How many of you have flown from, say, San Francisco to any place in the east, Chicago or New York, looked down and seen those circles? Okay, those are our central pivot irrigation systems. They're pumping water out of some aquifer, some water-bearing sandstone at depth, and then they have a long sort of a thing that goes around a pivot like that and sprays water, and so they're irrigated. These are irrigational things. So in fact, if you zoom in on them, you can sort of see this sort of round track. See how this almost looks like a section through a log or something? What's going on there is that pivoted right at the center there's a well right there, and they're pumping water out and spreading it all over the desert and raising crops. So what is water doing in the middle of the desert? Maybe it's not tremendously surprising because we're right next to an oasis. So clearly there's some source of fresh water. Any idea what it is? Okay, well, let me show you. If you back off and look at these things, they're not just everywhere, are they? See, there aren't any down in here. They kind of almost make a pathway with some branches in it. Does that help? Yeah. It looks like a river system, doesn't it? Okay, do you remember last time I showed you those radar images of the desert in Egypt, in which you could see valleys, a valley system that had been filled in with sand. Well, that's what's going on here. So if we back out here a little bit, let me show you a radar map. There's starting to be radar maps here and there. I mean, the Sahara is the size of the 48 United States. So it's not something that we have immediate coverage on. But let me show you a map here. So this is a map by a French guy. And here it is. And this is now a side-looking radar image. And what you can see here is actually, this is a river system. And here comes another tributary coming in like that. And they join here, and they run up this direction, and they're actually heading right straight for Kufra. Now, unfortunately, they didn't get coverage of the area where those pivot point irrigation things are. But my guess is probably what happens is that here comes the main branch, and it runs in there and flows like that, and here's a tributary coming in here, and here's another tributary coming in there. And this situation was discovered by people who were in the oil business. They just kind of almost accidentally discovered there's huge amounts of water down there, and it's what they call fossil water. In other words, it's water that accumulated in the bottom of these valleys back when the Sahara was wet. And since then, the Sahara has had sand blow over and filled in those valleys, but the water is still down in the bottom. And there's a really colossal amount of fresh water that's sort of ponded at the bottom of these valleys, and it's in the spaces between the sand grains in the sand that has filled it. And so they're pumping that out, and that's why this pattern here looks kind of a little bit like a river system. It's because it is a river system, or was a river system. Yeah, Yuli?
Sorry, how far down?
You know, I don't know. I haven't been able to find any specific information in it, but these kind of river valleys probably aren't terribly deep. You know, I imagine it's probably a few hundred meters down or something like that. So it's really very easy to get at. Michelle, you were going to say something? You know, that's an interesting thought. I hadn't thought about it, but there is a lot of microbiology in really strange places on the earth. So I wouldn't be at all surprised if there were, I never thought about it before, but I wouldn't be surprised if there were microbial communities down in that water in the sand. Yes, yeah.
If it's ponded water, does that mean eventually it's going to run out?
It's ponded. It's probably a place where maybe it was a lake or something in bottom one of those river valleys, and so it's just sitting there. It's not seeping out or flowing out, or it would have in the 10,000 years since the last time it was wet.
Continue farming there, or are they eventually going to run out of water?
They're farming there, and it looks like when we were in Libya, this discovery was made, and the time they said there were many years worth of Mississippi's flows of water. So I don't know what the actual amount of water is. There's a colossal amount of water. It's not being replenished, so it will be used up, which is actually what's happening under Tucson and Phoenix right now. I mean, they're using up water that's down there and is not being replenished. Yeah, Ricardo?
How do they separate the water and the sand? The sand is mixed in with
how do you separate the sand from the water? You just put down a pipe and you start pumping, and the water sort of gradually comes up through the sand, and you pump it out. Maybe it'll bring up some sand, but you could put it in a settling pond and it would get rid of that. Yeah.
So kind of combining the question about life, like astronomers use this whole water underground to think about life on other planets.
Yeah.
Everywhere became a Sahara, but underneath there's massive amounts of water.
You know, I hadn't thought about that one either, but this is something that people who are interested in life on Mars are talking about. Is there water down in the soil, not at the surface, but down out of sight, and could it be harboring lava? I hadn't thought about that. That's really good. Yeah. So an analogy to Mars. Okay, so the Libya has lots and lots of oil and very little fresh water. And so what the Libyans started doing, and this, I don't know, maybe this is 20 years ago or something, they built a huge pipeline from Kufra that goes up to the Mediterranean coast. Let me show you where that is. If we back out here, I tried to find it, but I think the pipeline is buried. So anyhow, here's Kufra. So the pipeline goes something like this, and it comes up to this point, and here it divides, and part of it goes to Benghazi, and part of it goes to Tripoli and the area around Tripoli. So that's their source of fresh water. So that was a really smart thing to do, to tap that water. So here's a case where you have the history of this country going back to the time when the Sahara was wet, 8 or 10 or 12,000 years ago, is strongly affecting what's going on in the country at the present time. So, again, that's the historian's approach to these things. Deborah?
Is oil rich because of how long ago that there's...
Okay, the oil comes back from much farther back. The oil's coming back from sometime in the Cenozoic or the late Mesozoic. So the oil is tens of millions of years old, and this water is probably 10,000 years old, something like that. So the oil's 1,000 times older. Okay? All right, so I want to show you something else now. So here we are up near the coast, and this is Tripoli, where Gaddafi is holding on, and this is Benghazi. It kind of looks like this entire eastern area is now under control of people who are rebelling against Gaddafi. And when you look over here, I think I showed you before, there are towns in here. Most of the towns in the hinterland have also fallen to the rebels. So it looks like at this point Gaddafi, if he's even alive, controls Tripoli and nothing else. And I wanted to show you something here that again is part of the historian's view of this, and that's why these places are so different. You know, you read in the newspaper, Tripoli the capital, Benghazi the second city. You know, it's kind of like, I don't know, New York and Boston or something like that. That's the way it sounds, or Los Angeles and San Francisco in California. But in fact, they are extremely, extremely different. And the reason is historical, and it goes way, way back. So let me see now if I can find, I think we're finished with this. Pardon, I had a little bit of trouble before. This is the one I wanted to show you. Okay. All right, hey, that worked better than I thought it would. Okay, so what I wanted to do was to show you some of the history of Libya and why that suggests that the people in the East, not only do they not like Gaddafi, they probably don't even like the people in the West very much. And this has huge implications for whatever will happen after Gaddafi. If Gaddafi does fall, which is looking more and more probable, what will happen next? And it really looks like they're in for a lot of chaos there, because Gaddafi had made sure that he was the only national power or national institution of any kind. There's basically nothing. There's going to be a terrible power vacuum whenever he's out of there. But just let me show you something that I just sort of automatically do in a case like this. I get out my historical atlases. Now, I don't know if any of you like historical atlases. I love them, and we've got quite a collection at home. But there's a couple there's a set of them, and if you're close enough to the front, you can see here, it says the Penguin Atlas of Ancient History by a man named Colin McEvedy. These are a series of little paperback atlases like this, and if this appeals to you, you might really like having this set. They're not terribly expensive, and they're just wonderful. They show you the same area again and again at different times. And so I'm going to show you some things from his ancient and then his medieval history atlas. So here's the situation in 560 BC. So we're back even in we're in Greece, not as far back as the Bronze Age, but further back than Aristotle and people like that. But here is Carthage, or Tunis is there, and then you come down, and Tripoli is right there. Did I just lose it there? Okay. And this is that Gulf of Sirte, and then this is Benghazi right over here, and then you go over to Egypt, and there's the Nile that David told you about. Okay, so the point I want to make is that this Sirte Gulf, which separates the eastern and western part, has been a boundary between cultures almost forever. And just to kind of show you that, at this particular time that we're looking at, Tripoli was run by Carthage, where modern Tunis is, and this area around Benghazi was a dependency of Egypt. So now if we go on, that was 560 BC, now we're at 480. Check it out. Carthage now still has this area over here, but now this Egypt has been temporarily conquered by the Persians. So you've got a complete gulf there between Carthaginians and literally a gulf between Carthaginians and Egyptians. Keep going on, that's 480 BC. Here's 375 BC, we're 100 years later. Now you see the Persians have lost out here, but the Greeks are moving in. And this is the fundamental difference between the western and the eastern part. The western part was for a long time sort of in the orbit of Rome and the Italians and the Latins. And the eastern part was always sort of in the Greek sphere. So they've got this differences between them that goes way, way, way back. So that's 375 BC. Here's 323. Now you see Alexander the Great has conquered his empire, and it includes Benghazi. And Tripoli is still part of Carthage. Keep on going. Now the whole thing has been finally unified under the Romans. But still, Greek was the language of Eastern Roman Empire, including Benghazi, and Latin was the language of the western part, including Tripoli. So they're unified now, but still culturally different. And there were, this is an amazing thing about Libya, it has these incredible Roman cities. So for example, this is Leptis Magna, that's about 100 miles east of Tripoli. And there was a very important Roman emperor named Septimius Severus who was born in this town, and when he became emperor he made sure that his town had a lot of fancy architecture in it. So this is a brief period now when Libya was united under the Romans, but now things start to separate. Now Rome is in trouble, and they're making a clear distinction between Eastern and Western Roman Empire, and you see the boundary goes right between the two. And now we're at the point where the Eastern Roman Empire, based on Constantinople, modern Istanbul, is still active, but now look what's happened. The Vandals, who were Germanic people from up in here, have come all the way down through France, through Spain, all the way around here, and they now have a kingdom based on Carthage, and it includes Tripoli. So now you have Greeks in the east and Germans in the west. And now the Eastern people took it back for a while, but now here's the beginning of the Arab conquests, and now they've come across the whole thing, and you'd think, oh well, it was all united under the Arabs, but in fact, as you go on, you'll see there's always a break between one ruling one regime and another. So anyway, you could keep on going like that. There's just always something there. So anyhow, when you see something that's going on at the present time, to me, it always makes sense to go back and look at the history and try to understand what historically underlies the events that you're seeing in something like the rebellion that's going on right now. Any more questions about that before we go on? Yeah, Michelle?
Does that geological divide influence how politics are shaped today, or is it? That's the Gulf of Sirte. Actually, when those were actually separate kingdoms called Tripolitania in the west and Cyrenaica in the east, and they were brought together, maybe a couple of hundred years ago by the Turks, and then later by the Italians, and then it's kind of hung together, but it's really a country that's made out of two very dissimilar peoples. Not to mention that there's a third chunk down in the desert where people haven't got any use for either of the ones near the coast. All right, good. Okay, so I can't resist showing you those things, but let me show you something else now. That's the one I want to do. Okay. No, I didn't want to do that. I wanted to do this one. Sorry. Okay. Where's that coming from? I don't want that. How do I get rid of that? Sorry. Try this again. Okay. Just a reminder, y'all, if you've been following your schedule, you know we have a quiz coming up, and it'll be just like the one last time, only it'll be on things since the last one. Okay? And then we'll have some discussion after that, and it kind of depends on how far I get today, what we'll do. All right, so everybody's aware of that? Good. Okay, so leaving Libya, coming back to the Earth history, I've talked with you quite a bit about cycles in Earth history. And what I'd like to do now is to show you a different kind of thing that happens in Earth history, and that's the occasional event. Just as the unrest in the Arab world right now is an event in history that's taking place presumably over a brief span of time, we don't know. But there are similar things that happen in Earth history, and I want to show you a couple of really cool ones today, the ones that I find just absolutely fascinating, and I hope you will too. So the first one is about the Ordovician. Ordovician, if you haven't looked at your time scale recently, Ordovician is roughly 450 million years ago. Remember that at 542, that's when you have the sudden appearance of all of these
fossils with, clearly that animals were starting to have hard parts, maybe to keep from being eaten by trilobites with eyes. I've mentioned that to you before. But the first of those periods after the fossil records get started is called the Cambrian, and the second one is called the Ordovician. And so what I want to do is to show you something about the personality of the Ordovician, because I've never worked on it myself, but I'm fascinated by it. So let me show you a story, and then I'll show you something much younger that comes back to about 10,000 years ago in this country. So we're going to go to Sweden. So here's the beginning. It's an impact story. And it's an impact event of a very special kind. And I want to start by asking you this question. How likely are asteroids or comets to hit the Earth? And the answer turns out to be very unlikely, especially if they're big ones. Little ones frequently. Big ones, very, very rare. So here's the situation. Here's what the solar system looks like looking down on. Here's the sun, and here's Mercury, Venus, there's Earth, Mars, and here's Jupiter. Between Mars and Jupiter is this big belt of asteroids, which are little tiny planets. Mini planets, right? And there's some of them that kind of ride out here a little bit in front of and a little bit behind Jupiter, but they don't need to concern us. So what I want to do is just think about these right in here. And each one of these now is on its own almost circular orbit around the sun. It's an ellipse, but very close to it's an ellipse, but close to a circle. But the point is that, picture this little guy here. He's got his own circle going around the sun. And as long as he stays on that, the chance of that hitting the Earth are 0. He never comes close enough to hit the Earth. Okay? So even though there's lots of things that you wouldn't want to hit the Earth out there, almost none of them have any chance of hitting the Earth. Okay, so what happens if we now look at the orbits of some of them that don't stay where they ought to? Some of them come inside. There's a small fraction that are called Earth-crossing asteroids, so that their orbit carries them inside the orbit of the Earth. So this is what some of those orbits look like. So there's the sun right there, and there's Mercury, Venus, here's Earth, and these are orbits of things that could conceivably hit us because they come inside the Earth's orbit. Now that looks pretty scary, doesn't it? Okay, it doesn't need to be scary because each of those objects is just tiny on the scale of the solar system. And the Earth is also tiny on the scale of the solar system. So the chances of being hit by one of these things are very small because they have to be, think about it this way, their orbits have to intersect or you can't have an impact. And then even if the orbits intersect, the Earth and the asteroid have to be at the point of intersection at the same time, or there's no impact. So even though that looks scary, it actually means that they're very unlikely to hit us. So to give you an idea of how unlikely, this is going to come back to the Ordovician. Trust me, I'm trying to show you. I'm trying to set this up so that you see how improbable something might be. Okay, so here is the moon, and there is Venus in the night sky. All right, now Venus is about the size of the Earth. So if you were an asteroid, if you were an anthropocentric asteroid that had a real thing about the Earth, you just really didn't like the Earth at all, and you were going to try and hit it and cause all sorts of bad trouble, that's kind of the target you'd be looking at over the scale of the solar system. You're trying to hit something the size of the Earth, which is Venus, or something the size of Venus, at this very long distance. So when NASA or the Russians send a space probe to Venus, you don't just take aim and shoot it and off it goes and then eventually it hits. That's too hard to do. So what NASA has to do is they keep following it and they see how well are we doing. Well, we're going to miss a little bit to that right. So they deflect the orbit, and then they get a little closer and they deflect it again, and they keep kind of adjusting it. So it's hard to hit something at solar system distances. And let's think about, I think I already mentioned this, but if you take your fingers like this and kind of loop them together so that they're linked. Now imagine that's the orbit of the sun, the orbit of the Earth and the orbit of an asteroid. If those two orbits don't intersect, there is zero chance of an impact. But even if they do intersect, you kind of twist them around, imagine you had infinitely thin fingers, right? Then you still have to have the Earth and the asteroid at the same point at the same time, or else they miss. So this is really hard to hit. Okay, so clearly this does happen occasionally because there have been big impacts. But we have, 4.5 billion years in which to have just a few of these impacts, so they're very unlikely. Okay, so meteorites are rocks that have fallen from the sky. So they are pieces of an asteroid or something that fell on the Earth. So we have a fair number of these. And I want to just show you something about how asteroids, how meteorites are found. So, for example, not for example. The point we make here is that there are 4 settings in which meteorites have been found. Okay, the first setting is that originally most of them were found just something lying around on the ground. So if you're out walking in the field someplace and you come across a sort of a chunk of what looks like burned out iron, you pick it up because it's unusual, and that might be a meteorite. I've looked at a lot of rocks in my life. I've never happened to find one, so there aren't that many. And some meteorites are made of iron, so you're more likely to find those, and some are made of stone, and they kind of look like any other stone, so people are less likely to find them. So a while it looked like there were more iron meteorites than stony ones. Turns out it's the other way around. So that's how most of them were found until recently. Just occasionally one is observed falling or found just after landing. This is a case in New York State of a meteorite that went through the back of a car here. And so one of my former students who teaches at Columbia went running out there, and they investigated this thing. And anyhow, so occasionally one is actually seen to fall. Right? That's the second way you might find one. The third way is that a very tiny number of meteorites have been found in sedimentary rocks. So imagine this is a meteorite that fell maybe 100 million years ago and fell into a place where sediments were accumulating. And the sediments kept accumulating and accumulating like that. And then some geologist goes out now, or somebody looking at a quarry, and finds this meteorite. And the meteorite didn't just fall recently, it fell 100 million years ago or something like that. So they're called fossil meteorites, and they were extremely rare. And until recently, I think it was thought that 6 of these had been found. And again, I've spent much of my career as a research geologist looking at the kind of rocks where you would expect the highest chance of this sort of thing being found. I've never seen one. So they're extremely, extremely rare, fossil meteorites. Then the fourth way that you ought to know about, because it's so cold even, is that many have been found in Antarctica. So here's a geologist, and here is a meteorite lying on the surface of the ice in Antarctica. And here he's taken photographs of it, and he's going to collect it. And a huge number have been found on the Antarctic ice for a really interesting reason. Here's how it works. Here's a sort of a schematic cross-section to show what happens. Here are some meteorites, and they fall and they land on the ice. Okay, then if they fall in an area where ice is accumulating, in other words, there's more snowfall than there is evaporation, then they gradually get buried and buried. So this guy here, as the centuries pass, will follow along a route like this, just as more and more snow is being added. And over in this area, it says ablation zone. Ablation means that the ice is evaporating, sublimating. And so here, the glacier is flowing from an area of ice accumulation here to an area of ice removal over there. So the meteorites follow along paths like this, and when they come to the surface, the ice around them gets evaporated, but they don't, And so they just accumulate, and you get more and more and more because they're coming up from underneath every now and just accumulating on the surface. So now geologists know where some of these places are in Antarctica, and you just go out there and they've collected vast numbers. And by doing this, it's become clear that the stony ones are much more common than the iron ones. And this is also wonderful because the rock, the meteorite, has been in deep freeze ever since it fell. So these things are absolutely perfectly preserved. No chemical reactions take place at all because it's just too cold. So it's utterly revolutionized what we know about the solar system from studying these ancient meteorites that were formed right when the solar system was formed. Okay, so that's the background you need. Now I want to take you to a place in Sweden. So this is a quarry at a place called Kinnekulla, or Julie could probably pronounce it better because she's a Swedish major. I think they say Kinnekulla for some reason. Local people do. At any rate, this is made of limestones that were deposited slowly in deep water. And a few years ago, a fossil meteorite was found here, raising the global total to 7. Now, I don't hear anybody drawing their breath with amazement or wonder at this, but just you wait. Okay, so let me tell you the story of that meteorite. Okay, it was found by a guy named Mario Tassinari, and Mario is an Italian guy who was in Italy right after the Second World War. It was very, very hard to find work, so a lot of Italians went to other countries, and Mario emigrated to Sweden just to find work, and he married this nice lady named Inger, and he's lived in Sweden ever since. And here he is. This is a quarry face in the quarry at Kinnekulla. And this is the meteorite right there. And what's going on is that's meteorite, and then this is oxidized limestone around it. It's oxidized, so it's basically got iron oxide in it, which is like rust, which colors those rocks red. But the meteorite itself, when it came in, was not oxidized. And so there's sort of a reaction rim around it. So all of this is limestone that was red, but by reaction with the meteorite, the iron has been reduced, so it's not rust anymore. So it has this sort of a white circle around it. So that's what Mario found, and he thought this was a meteorite. You know, but he didn't know for sure. So he suspected it was a meteorite, but he'd never seen a fossil meteorite because almost nobody in the world has ever seen a fossil meteorite. So he called up a Swedish geochemistry professor named Birger Schmitz. And Birger had been here at Berkeley working with Frank Asaro, you know, the guy who did the iridium measurements on our work on the extinctions. So I'd known Birger from when he was much younger and living here. And so Birger studied this candidate fossil meteorite that Mario had found, and what they saw was that it was all just rotted. The minerals in it were chemically rotted. They were altered, so you really couldn't tell from the minerals. But what he found was that one kind of mineral in there called chromite. Chromite is an iron chromium oxide mineral, and it wasn't. Those had not reacted chemically. They were absolutely fresh. And so Birger knew all about those things, and he did careful analytical work on them. They found out what all the trace elements were, and basically they could show that these chromites did not come from the Earth. They came from a meteorite. That's the only place they could have come from, because they knew all about the chemistry of chromites in meteorites. And in fact, it was not only from a meteorite, it was from a particular kind of meteorite. So there are probably about 20 kinds of meteorites that experts make, that make this classification, and it's based on the details of the chemistry of the thing. And so this is a kind that doesn't matter what it means, but it's called an L-chondrite, and we'll come back to that in a moment. So anyhow, I thought you might really enjoy that. Isn't that a wonderful story of, yeah, Natalie?
7 maybe.
Pardon?
7 the global, what did you say? global total to 7?
Yeah, because this is of fossil meteorites, not the ones from the ice in Antarctica, but the ones that had fallen a long, long time ago and were preserved in sedimentary rocks. Remember earlier on I said I think there were 6 known fossil meteorites. So anyhow, this is 7, and I thought you'd like that story. But there's more. And what makes this story begin to be special is that after a while, Mario found another fossil meteorite. He lives real close to this quarry, and the quarry has lots of really good fossils, biological fossils in it. So he spends a lot of time in this quarry, and after a while he found another one. Well, that was pretty exciting, from 7 up to 8, just like that. And there's a fossil on the right-hand side, and on the left-hand side is the meteorite. So, of course, he calls up Birger, and he says, Birger, I got another one. And would you like to look at it? And Birger sort of yawned, and he said, sure, I'll come up and look at it. But Birger figured that it wasn't a big deal, because when meteorites enter the atmosphere, they come in real fast. You've probably seen them as a streak in the sky. How many of you have seen the meteor streak in the sky? Okay, all right. That is a bit of an asteroid or comet that's come through, and it's burned up by friction in the atmosphere. And so when one of these things hits the atmosphere, there's a lot of stress, and so this is a numerical computer simulation, but this is an object that came through, and now it's coming in. You see the atmosphere is getting thicker and thicker, and you see it's sort of broken up into all these kind of pieces. So Birger figured this is not going to be a big deal. It's just another piece of this meteorite. But he went up anyway, because Shinnekula is a nice place to go, and he liked Mario, so he went up there. And so he expected it would be found in exactly the same bed in the quarry. Let me come back to that. Remember Steno, who showed that layers of rocks are piled one on top of another like that? Okay, so that means that any bed in this quarry was all deposited in the same interval of time. And if this is a bed deposited in one interval of time, the next bed is entirely younger. So Birger figured, well, the first fossil meteorite was here, and the next fossil meteorite will be someplace else in the same bed, because it came in and it was, it broke up. But that wasn't the case. And here's where the story starts to get really interesting, because they were from different beds. They were in different beds, so the two pieces of meteorite could not possibly be the same age, and therefore they could not be fragments of the same incoming impactor. So this question faced Mario and Birger. How could a single quarry contain 2 fossil meteorites from 2 different falls of 2 different ages, when meteorites of any kind are so rare? So this is a mystery. Here's a really good mystery. Scientists love mysteries like this, right? Okay, so let me show you part of the story. It turns out this isn't all of the story, but I want to show you this because this lets you see what geologists do when we're trying to figure out Earth history. So partly the reason why a single quarry could contain 2 fossil meteorites, partly it has to do with the nature of the limestone. And that limestone was deposited, first of all, in deep water, and second of all, very slowly. So a lot of time is represented by the beds in the quarry. So this helps you, if that quarry was basically sitting there catching meteorites for a longer period of time, it has a better chance of finding, this second meteorite. So I want to show you how we know that these limestone beds were deposited, first of all, in deep water, and second of all, very slowly. So this is Maurits Lindström, who was a Swedish geologist who was Birger's teacher. And when Millie and I went there a couple of years ago, we got a chance to go to this quarry with Mario and Birger and Maurits Lindström, which was really a wonderful experience. But he's been studying this limestone for a long time, and let me show you the sort of things that he found out about it, because again, this is what geologists do. So first of all, this is looking down on a bedding plane, and these funny looking things are fossil shells. And they're fossils of this guy who was called Orthoceras. And he's related to the chambered nautilus and ammonites. So the chambered nautilus has a shell that's exactly like that, only it's wrapped around in a spiral, right?
So this is like, it's related to the chambered nautilus, only his shell didn't curl. So they had these long, delicate shells like that, and I think you could picture that if those were deposited in a place where there was currents and waves and storms and things disturbing the bottom, they'd all be broken up. And indeed, other places you find these things, these orthoceras shells, they're all broken up because the conditions were so turbulent and disturbed. But in this place, they all just sit there and they're utterly unbroken. Now, the only way that you could get that was if they were deposited in deep water, because the deeper you go in the ocean, the less effect waves and storms and currents have. So the water gets quieter and quieter and quieter as you get deeper down. So these things had to be deposited deep in order to explain why they don't have broken shells. So that's the first thing, they're deposited deep. But then the second thing that Maurits Lindström had figured out was that they were deposited in very slow sedimentation rates. And it's, so this is a sea bottom where occasionally a little particle of something comes down. And over millions of years it builds up limestone, but very, very slowly. And here was the evidence, which I think was really cool. So he knew that these were deposited with very little sediment coming down because there are no animals that live attached to the bottom. So here are two kinds of animals, brachiopods and crinoids, that live attached to the bottom. We aren't used to thinking about animals living fixed because land animals are almost always move around. But on the sea bottom, there are animals. These aren't plants, they're animals. And they live attached to the seafloor. And these guys can only survive in a situation where there's lots of sedimentary particles coming down, some of which would be good stuff to eat, right? And so this guy's sitting there, and any good stuff that falls there, he catches it and eats it. But if something falls over here, he can't go and get it because he can't move. He's anchored to the bottom. So if you have these anchored guys, it means that there's a lot of sediment coming down so they can stay alive. There aren't any of those. The only thing that you find on the bottom is guys like trilobites here who had legs and could walk around, so they can go and get whatever comes down. So it's the nature of the fauna that lived in this situation that tells you that this was a very slow sedimentation rate. Okay. Once you say that it's very slow sedimentation rate, then that helps you because you have more chance of finding a fossil meteorite. Okay? All right, so now let's go on and see what happened. There was another thing that helped, and that is that this is ornamental. Limestone is being quarried for ornamental stone, stone that's used in, to make walls and floors in buildings. And so it's all being cut into 2 centimeter slabs, like an inch thick. So this means that they've gone through this entire, everything that's been removed there has been sawed that thick. They've gone through this entire body of rock and sliced it into these thin little slabs. So if there's a meteorite in there, if it's bigger than about that, they're going to find it. And actually what happened after they found the second one, Mario talked to the quarry guys, and the quarry workers, they spend all day slicing thick rocks into thin rocks, and they told them about these meteorites, and so the quarrymen found this really fascinating, and so they're always on the lookout. And if there were any more, they would come and tell Mario about it. So anyhow, so here's the summary up to this point. 2 fossil meteorites that fell separately were found in a single quarry because the sedimentation rate in these deep water limestones is very slow, so the quarry represents a long interval of time, and because the whole quarry full of rock is being cut into slices. Okay, cool story? Well, let's keep going. Oh, I forgot to tell you that the second meteorite was also an L-chondrite, but not the same L-chondrite because they were deposited at different times. Okay, here's the amazing thing. So Mario and the quarry workers keep finding more and more fossil meteorites in many different levels. So here is the here is the whole sequence of limestone beds in this quarry. They each have, the quarrymen have names for each bed, and this is how thick they are. So that one is a little over a foot thick right there. So basically they've got several feet of limestone, and they keep finding fossil meteorites. So this schematically showing where they found them. This bed has lots and lots and lots. And as of last time I checked, in December of a year ago, more than 90 fossil meteorites had been found here. And as you see, they're in all these different beds, so they're coming at different times. How can this be, when I showed you at first how unlikely it is that anything hits the Earth? And this is one quarry in Sweden. You would imagine that this is probably worldwide. So it looks like the Earth was just absolutely in a hailstorm of meteorites for this interval of time, which is a few million years. And what's more, every single one of them is an L-chondrite. Is that a cool question? No. I think what I'm telling you right now is this is probably the first truly great geological discovery of the 21st century. You know, there's going to be more, but this one this has got my vote as the most amazing discovery of the 21st century in geology so far. Okay, so let's think about that. So this limestone from that quarry has been used all over Sweden. So Birger, who's here, can sometimes do field work in public buildings. So here he's pointing to a fossil meteorite in the ornamental stone on the floor of an airport that he took us to when we were leaving. He tries not to collect those, but sometimes it's hard to resist. But he's found several in public buildings in Sweden. Okay, so let me go over here with where we are in this story right now. Remember, what we're talking about is an amazing event in Earth history. It's an event in which this vast number of meteorites, all of the same kind, fell in Sweden and presumably everywhere else. Okay? So, if this huge number of meteorites fell in a single quarry over an interval of just a few million years, the whole Earth must have been caught in a hailstorm of meteorites. It's really hard to figure out any reason why meteorites would be particularly attracted to Sweden. Okay? Some people major in Swedish and they might have a different view, but anyway, presumably it's happening all over the world. The calculated fall rate is at least 100 times that of today. It's probably very much more. I mean, this is the most conservative estimate. Okay, and Birger's analysis of the chromite grains shows that every single one of the fossil meteorites is an L-chondrite. So this is some very unusual event that nobody has ever run into before. Okay, so what do you do if you're a scientist? You got something like this. You got to check and make sure you aren't being fooled somehow. Can't imagine what could do it, but they felt that they needed to find another site of the same age somewhere else in the world and see whether it had a lot of fossil meteorites in it too, so they could exclude some weird situation in Sweden, which they couldn't imagine what it was, but you have to do these things. So Birger looked all over the world, looked in the publications of the geology all over the world, trying to find if there was another place that would have a quarry in this kind of slowly deposited limestone somewhere else in the world, and there just wasn't anywhere. And I helped him look in this country. Couldn't find anything. So finally what he found was a situation in China where they don't have any quarries, but they do have rocks of the same kind, these very slowly deposited limestones of the same age, which they could tell by paleontology. So he teamed up then with a man named Xiaofeng Wang, who is a paleontologist in China. And here I just have to take a slight side trip, because Xiaofeng Wang was also on this trip that we were on, and he told me, again, it's a sensational story. So it's about crinoids. Remember I showed you that picture? The crinoid is rooted at the bottom, it has all these sort of fronds that catch things that are coming down. So maybe some of you have seen this. Have you ever found these little fossil Cheerios? Anybody ever found those? If you lived in the central part of the U.S., in Indiana or someplace, you'd find them all the time, and they are parts of the stem. So this stem here is made of all of these little Cheerios stacked one on top of another and held together with some sort of organic material, and then there must be some kind of a spinal cord or something that goes up through it. At any rate, the crinoid has a stem or a column made of these columnals, and then it has this thing called a head or a calyx that has all of these arms sticking out, and that's where the guy does his eating. So this is what a crinoid looks like, but again, as in the case of the orthoceratids, if these are in shallow water, after they die, the waves and the currents break them up. So I've found lots and lots of columnals, these little things, but I've never found a whole calyx. And so I asked Xiaofeng Wang if we were talking about crinoids, I said, have you ever found a calyx? And he said, oh yeah, I found lots of them. And he said, I've found them. I said, how about, were they still attached by the stem? He said, I found stems 10 meters long. Okay, 10 meters long is here to that wall, right? I said, how could that possibly be? And then he told me this incredible story that I just have to share with you because it's such a neat example of what evolution does. Okay, so here is Xiaofeng Wang, or one of his people he's working with, I'm not sure. And this is a crinoid. This is a bedding surface of a deep sea sediment, and they've cleaned off, just like an archaeologist, they've excavated off all the beds above it, so they've got a single surface. This was all the seafloor at a particular time, and can you see the stem coming up here like that? And here is the calyx, and here are all the little tentacles sticking out of it. Isn't that fantastic? Huh? Yeah, mostly they're tiny, but this thing's huge. How could this exist, and how could it be preserved? Well, he told me something about crinoids that I'd never heard before. So most crinoids live on the bottom, and they're sort of rooted in the sediment on the bottom, and they have the column that comes up, and here's the calyx up here catching whatever sediment comes down. So most of them live rooted on the bottom and stretching upward into the water column, but not all of them. So here is the situation. So there were crinoids at a certain time that lived on floating logs. And so they were not rooted in the sediment on the bottom, they were rooted in this floating log. And what you see here is each one of these is a little individual crinoid. They're probably all brothers and sisters, I guess, but there are ones with short stems, and there are ones with medium stems and long stems and very long stems like that. And so what these guys did was they rode on this floating log, and as the floating log drifted in the wind across the seafloor, these guys were down there, and they were sort of collecting any nourishment that was in the water at any depth, and living that way. So it was a great way to work, and so they hung down from floating logs. Now then the thing is that when the floating log sank, eventually a log will get waterlogged, and then it isn't float anymore, and it sinks. And so then there's some places on the bottom of the ocean where there isn't any oxygen. Those are called anoxic zones. And if the log fell into the anoxic zone, there's nobody down there living. If it's deep water, it's very quiet, and there's no scavengers able to live on the bottom because there isn't any oxygen. And so the log full of crinoids falls to the bottom, and it just lies there, and there's nothing to eat it up, and eventually it gets covered by more sediment. And so this is the situation in which these things were found. And so this was... This is in the Triassic, which is like about 200 or 250 million years ago. And apparently this was a very popular mode of life for some groups of crinoids until the evolution of little boring clams that also live in the log. And those guys would eat the log up really fast, and so it would sink too soon for these colonies of crinoids to develop and live. So floating logs were a great way for crinoids to live until there weren't any floating logs that floated for very long, and so these groups of crinoids all died out. But I had to put that into this. It's not directly related to the meteorites, but it's such a neat story of evolution of life. I can't resist telling you about it. So yes, Betty?
Where'd the clams come from?
The ones that bored in it? Well, I mean, how did they get into the logs? Oh, probably in all these cases, many of these animals that live in the sediment on the bottom or rooted, they have larvae that float. So the very young animal, the larval stage, is floating, and so they produce very large numbers of larvae, which then kind of float all over, and then when they mature, then they take up residence wherever they are. Ryan, you're going to talk about that.
Oh, I was just going to put in a plug for it. This is kind of an interesting paleoecology question. So paleoecology is a field in which people reconstruct not just what used to live, but the interactions among extinct organisms that they can reconstruct larger fossils. And here's a really interesting one, because where do the logs come from? I mean, this tells you something about that you have to have these kind of large stands of forests in order to kind of produce these logs, some of which end up in the ocean. And it tells you that the crinoids somehow find the logs that are floating around in a very big ocean in order to live on them, right? And so what that tells you is they probably have very long larval periods to be able to put out larvae that will then travel around the ocean all over the place, and occasionally one will find a log and land on it. Either that, or they don't have a larval period at all, and they just kind of bud off. And once one finds a log, they colonize the whole log because that's a good place to be. And crinoids are echinoderms, like sea cucumbers and sea stars and whatnot. Echinoderms have a specialized type of larvae that lasts a really long time, so that actually makes a lot of sense. You could spend 70 to 90 days in the water column if you're the larva of an echinoderm now. And that may have been true even in the Ordovician or in the Triassic. So just one picture like this kind of can bring up a huge number of topics in your mind if you just think through.
That's neat. I didn't know about those, how long those larvae lasted. Thank you. Yes.
From looking at the picture, I was wondering, are we sure that each one is its own organism, or could it be one animal that shoots off into a bunch of different,
Well, I think that's more, I think Ryan was sort of referring to that this was all colonized, this might have been all colonized by the descendants of a single larva. Yeah.
Could it be a single larva that shoots off into it instead of creating more larvae than
I'm sure that a crinoid specialist could answer that, but I couldn't. But yeah. But maybe here's a thing to think about as we're just passing by this. Thinking about the history of life, which we're going to get to next. If you think about how the history of life is conditioned on what kinds of animals and plants are around, and then things change. So coming back to Ryan's point that you had to have forests. If you didn't have forests, you couldn't have crinoids with this thing. So land plants appear in the Silurian, which is after our Ordovician. It's the next time after. And so you couldn't have these crinoids until there were forests to produce the logs. So that means you wouldn't expect these crinoids in the Ordovician that we're talking about, because there weren't any forests at that time. So these were not found, I should just make it clear, these were not found in the Ordovician quarry. These are from much younger things, from the Triassic. And so there's a window of opportunity then for these crinoids that hang from logs. And that opportunity window runs from the first trees until those borers start to eat up the logs and make them sink. Okay? Good. All right. So anyhow, couldn't resist that. So anyhow, they didn't have any quarries in China to go. We're back on the meteorite story. They were trying to check whether there were other places in that part of the Ordovician that had multiple fossil meteorites. Unfortunately, that was the only place in the world, apparently, that has quarries in the right kind of rocks. But what they did with Xiaofeng Wang was to go to outcrops, and they collected great big samples of limestones of the right age, and then they would put them in acid, just Mason's acid, muriatic acid, and dissolve the limestone and get out see whether there were chromite grains in them. And this is a really tedious job. Beer does a lot of this now. He has students who help him, right? And they dissolve these big chunks of rock. And what you can see here, this is the Ordovician. So this is from older to younger. Remember, this is done as a geologist thing, because these are the rocks piled up in sequence. And so here is the Ordovician, and these are various subdivisions of the Ordovician. And here's what you see in two places in Sweden, those quarries and then a nearby locality. And these dots show how many extraterrestrial chromite grains. EC stands for extraterrestrial chromite. And this is 0. So basically all through these things, they maybe got, no, there's 1 per, I don't know what these are. It's per kilogram of rock, that's it. So basically there aren't any until you get to here, and now you start to get these extraterrestrial chromite grains, the kind that come from alchondrites. Then you get back here and there aren't any more. Again, here you come along, this is in Sweden, in both of these, and then over here in China you get the same thing. So this tells you that even though you haven't found any meteorites in China, just because there aren't any quarries, the chromite grains tell you that the same thing is happening in China as in Sweden. Presumably it's happening all over the world, right? Okay, so what can this possibly mean? So here's the interpretation that they've come up with, how you would get this storm of meteorites. Imagine that in the asteroid belt, there's 2 asteroids, say a bigger one and a smaller one. This guy here, the bigger one, would have been an alchondrite. That's what they call the alchondrite parent body. And it was happily flying along in its orbit around the sun, not bothering anybody, and then it gets hit by another asteroid. And there have to be collisions in the asteroid belt every now and then. And it just breaks it up into smithereens, which is a technical term for what happens then. At any rate, so there would presumably have been billions or trillions of these fragments of the alchondrite. And some of those get to Earth, and those are what make for this storm. Okay, so now why would they come into the inner solar system? So remember, I had this picture earlier, and each one of these things is going around and around and around the sun. So if you have a collision here someplace, why don't the pieces pretty much keep going the same? Well, it turns out in astronomy there's something called a resonance. Now let me explain this picture too. This takes a tiny bit of explanation. Okay, so if we drew a cross section here from the orbit of Mars partway out to the orbit of Jupiter and spread it out, here we are. Earth and Sun are in this way. There's the distance of Mars, and Jupiter's probably over here someplace, okay? And so this shows kind of how many asteroids there are at each distance out from the sun. And what you see is that this belt across here is not a complete belt. It's a belt that has gaps in it. And the gaps are called resonances. And so this one right here is labeled 3 to 1. So that means that if you are at this distance out from the sun, every time you go around the sun 3 times, Jupiter, which is out farther, goes around once. Things that are out farther are going around more slowly. And so every 3rd time that you get back to this spot, there's Jupiter in close, and its gravity just gives you a tiny little tug. And so after many, many, many orbits like this, because Jupiter has another shot at you every 3 times around, you just can't stay at that distance from the sun. That's called a resonance. And so you see, basically these have all been cleaned out. There just aren't any asteroids at that distance. And there's others here. This is you go around 5 times, Jupiter goes around twice. And here you go around 7, Jupiter goes around 3, and so forth. Here's one where you go around twice and Jupiter goes around once. So those have all been cleaned out. Those are called Kirkwood gaps. And so any orbit, any asteroid that is in that particular distance orbit, it will be pushed into some other orbit by this repeated disturbances from Jupiter. And there's another one in here, and I confess I haven't taken the time to find out what this new resonance is. Maybe one of our astronomers knows what it is, but at any rate, this is also clean. This is the innermost edge of the solar system, of the asteroid belt. And so the interpretation is that that Flora is an asteroid which they think would be the largest fragment that was left after the L chondrite body was broken up in this collision. That it is out here, and that the asteroids that some of those fragments of asteroids were in this unstable zone, this resonance, and they were therefore disturbed and pushed into orbits, some of which crossed the orbit of the Earth. And there must have been an absolutely vast number of them in order for a small fraction to hit the Earth, and the small fraction be as many as it was. Because when you see that they've got close to 100 meteorites already from a little quarry that's maybe twice the size of the stadium up there, think how many must have hit the Earth. Okay, so this is something completely new. Nobody had ever heard of an asteroid storm before. But now I want to show you two other things that seem to support this story. So the first one is this is looking at the ages of known impact craters. Okay, now we're talking about much bigger things that fall, because those little meteorites the size of your fist, they don't make a crater. But if something that comes down that's you know, the size of this building were to hit the Earth, it makes a crater. And those are impact craters. And the one in Yucatan, the Chicxulub crater, that's a great big one that has been discovered. That's almost the largest we know on Earth. But smaller ones will make smaller craters. And if you plot plot the ages. Here are the ages. This is the number of craters. This is a histogram, so that's out to 60 million years. So this is how many craters are known from the last 30 million years, nearly 40. And you see it falls off as you go backwards, and the reason for that is not that there were fewer craters, it's just that the older they are, the less likely they are to be preserved and found. They will have been eroded or covered over. So if you fit a curve through that, it would seem like a nice sort of an exponential tail off like that, except there's one spot right here where there are several craters, far more than it looks like, and that's right in that time of the Ordovician. Right in that same interval. So that suggests that it wasn't just little guys that were falling, but ones big enough to make craters were also coming in that time interval. And then the other thing that's really neat is that these L chondrite meteorites, huge numbers, fell during the Ordovician. But that didn't completely clean up all of the fragments of this impactor. Some of them are still out there, and some of them are still falling now. And some have fallen on the Antarctic ice, and that's all within the last, few 100,000 years, so very recently geologically. And so those things have been collected, and you can actually do a radiometric date on those that tells you the age of a shock that hit it. Because what happens is if you have potassium decaying to make argon, and that's what you're using to date it, if you have a shock event, the argon will escape, because if it can get out, it will. Remember, it's a noble gas, so it doesn't stick to rocks, it'll escape. So you can actually date shock events in the meteorites past. And when you look at L chondrites, they always show shock ages of right around 470 million years, which is the same age as the Kinnicula quarry. So that tells you that even today, these things are falling, and they were also shocked in that time, just before the big mass of them was falling in Sweden. So Birger had fun in the quarry. He brought together two fragments of the L chondrite parent body. So the one on the left is one that fell in Africa. It was an observed fall, like the one in the car. Actually, it hit a kid on the head, and the kid was all right, apparently. But it had slowed down enough so that it didn't hurt him very much. But at any rate, that's an L chondrite that fell in 1992, and this is an L chondrite that fell in Sweden 470 million years ago. They're part of the same parent body. And this one got swept up by the Earth real fast, and this one has been in orbit for a long time before it fell. Okay, so there's one more bit to this story, and that is that you know from the T-Rex book that mass extinctions are disasters for the victims, but they're good for the survivors. So what you see here, this is a plot of the number of genera through time from 540 million years ago to the present. And so don't worry about these colors in there, that doesn't matter. The main thing is the top line here. So here is the Cretaceous Tertiary extinction. What you see is the number of genera drops to about half of what it used to be, and then it recovers rather quickly. And here is another mass extinction, here's another one right there, here's another one right there. And so Birger immediately wondered, was this impact storm at the time of a mass extinction? It turns out it's not, because there's a mass extinction at the end of the Ordovician. But what you see here is an amazing thing. This is the greatest increase in the number of genera. Not a mass extinction. This is a sudden increase, and there isn't any mass extinction before it to have triggered. And it looks like that took place at just about the time of the impact storm. So it may be in a way that nobody can yet figure out, that this bombarding of the Earth with all of these little things, nothing big enough to cause a mass extinction, but constant pummeling of the Earth may somehow be responsible for this greatest increase in the number of genera. Nobody knows why yet. It's an observation that the timing is about right. And that previous graph is a little bit generalized to show any details, but this is a case where they've actually gone out and collected brachiopods. Remember those guys that were rooted on the bottom I showed you earlier? And there is one jump in the increase. This is the increase in diversity, and that happens right at the same time as the shower. But the problem is that there was an earlier big increase here, and that's before the shower. So right now, if you don't see how this all makes sense, neither does anyone else. But it's really a cool problem to be thinking about. So there's the whole story, and I want to show you one last thing. So this there's a sad moment in this story. So a few months ago, Mario, who we just really liked him enormously. Mario was diagnosed with cancer, and terminal cancer, and it was thought that he probably had, I don't know, a month to live, something like that. And Birger was utterly shaken up, and so were we when we heard about it. Well, what happened was that turned out to be wrong. And it turned out Mario did not have cancer. Mario's doing just fine. And about a month ago, Mario received news that he is to be awarded the degree, an honorary doctorate in geology and paleontology from Birger's University at Lund, which is pretty good for a guy who went as a guest worker to Sweden in the 1950s, has very little education, but is a wonderful geologist. So my last picture is Mario getting the news that he's going to be a doctor in May. If Millie and I can get there, we will. We hope to. So there's my story of a great event in Earth history.